This is lecture one. We're going to talk about normal stress and shear stress today and some of the applications, learning about those stresses. Normally, we would calculate the normal stresses and shear stresses based on external forces that have been applied to a structure. And in a design situation, we might use what is called the allowable stress to determine the cross-sectional properties or other dimensional properties of the structure. It was one of the first generation of design philosophies that existed with engineers many years ago. We've kind of moved on to other types of design philosophies beyond the allowable stress method, but I think it's a good place to start with the discussion, especially in a design setting. This is not a design course. This is really a course intended to do the analysis of the structure. But I think it's always good, at least, to bring into the discussion how you might use these calculated stresses to design components and structures. So let's start with the normal stress here, and it gets its name because the stresses are normal to the cross section. And so I have this member here in the bottom left corner. It's being pulled on in a tension manner, and maybe you think back to your trusses in your statics class. You have some sort of external force, and there is a member that's in tension, and we know from statics that there's an internal force that keeps this member in static equilibrium. If we were to sum forces in the y direction, we would see that these forces add up. And so they're both called P because the external force P is equal to the internal force P. Now, the thing to remember about this class and throughout the whole course is that stresses develop based on the internal forces. Okay, so we're going to have several types of external forces that we have on our structures throughout the course, and there will be various internal forces that we'll learn about as well. This is just one of those internal forces, and this internal force is normal to the cross section, and so it's going to develop what are called normal stresses. And so what this picture is here is just kind of a blow up of this area. Okay, and what we have here is a picture of what are called uniform normal stresses. This is the assumption that's made, is that as we pull on this member, there are internal normal stresses that develop. And they're all the same magnitude, so that's why we say it's uniform. So if we were to look at a particular area, a small area, differential area, or some sort of delta A here, where there's a certain width and length to this square, such that it might have units of something like inches squared. Be very small, wouldn't it? But it would be with units of, say, inches squared or millimeters squared. That would be the area, obviously, that the stress would act on. Now, the stress, the units for stress are something in the, use something like pounds per square inch or kips per square inch. One kip, as you recall, is 1,000 pounds. It could also be in SI units, where it may be newtons per meter squared. So that would be a Pascal. So we have a force divided by an area. That would be the units on sigma. So if we were to take the normal stress and multiply it by the area, delta A, we would have, for instance, if we're using pounds and inches, pounds over inches squared multiplied by inches squared. The inches squared cancel, and we're left with units of pounds. And so we would have some sort of differential force or incremental force, however you want to look at this, as some small little force. And if we add up all of these delta F values. We add up all the delta F values. In other words, there's going to be another delta A here and another delta A here, and we add up all of the delta F's over the cross section. They would sum up to this internal force P. Okay, so we sum up the forces here, we get P, and obviously if we sum up all of the delta A's, that would be the total cross-sectional area. The normal stress sigma, this is a Greek letter sigma, lowercase sigma, and that being constant just would remain by itself as sigma. Okay, so we can then write this expression for sigma, the sum of the delta F's divided by the sum of the delta A's, would be a definition for the normal stress. Now, obviously, we know what the numerator is. That's just equal to P. And the denominator, we know that is just the cross-sectional area. So just by this very simple example, we can come up with our first normal stress equation, P over A. Okay, and so we're going to use this quite a bit throughout this course, so you'll want to refer back to this P. Now, P is just a generic internal force. It could be any letter. P is not really, it doesn't have to always have the letter P, certainly for that internal force. You know, we're kind of used to seeing cross-sectional area represented with a capital letter A. That's pretty common. Okay, but notice the units are in what we would expect them to be, some force divided by the area. Now, if we apply this idea to this now a little bit more complicated structure, we have external forces applied at the two ends, 22 and 12 kilonewtons. And then we have these kind of rigid disc here where we're applying a total of 18 kilonewtons here and a total of 8 kilonewtons here. And if you were to apply the equation, the sum of the forces in the x direction equal to 0, you would see that this structure is in static equilibrium. Now you might wonder, why do we have these two forces applied like this? And it's really to prevent any sort of bending of this rod or this bar. Okay, we could have just put 18 kind of in the middle here, but it's kind of hard to visualize how you apply 18 to this solid disc without somehow bending the bar in a way that we don't want to bend it. So if we divide it top and bottom and apply our forces this way, then we're not going to induce any sort of bending moments in the bar. It's just a convenience and a way to look at this so we don't have to consider bending of the bar at this particular point. Now, we're not going to concern ourselves with what's going on with the ring or with these discs here, or even the rope for that matter. We're just going to look at the maximum stress that occurs in either section AB or BC or CD. Okay, so the dimensions for the bar are 35 millimeters and then 10 millimeter thickness, and that's constant for all three of these. Okay, so the question is, how do we determine the maximum normal stress in the bar when it's subjected to these forces? Now, the main thing to remember from the first slide is that our stresses come from internal forces. And so that's one of the reasons why you spent so much time in your statics class learning to draw free body diagrams and finding internal member forces, is that we need those internal forces in order to determine the stresses that develop in our bar. Okay, so let's have our bar down here at the bottom, and let's now look at the free body diagram of each section, AB, BC, and CD. So the first free body diagram, we're going to isolate this region here. and draw that free body diagram. So we're going to cut the section somewhere between A and B, and we're going to apply equilibrium to that with our external force and internal force, and it's very easy to see with that particular problem. The internal force between A and B is 12 kilonewtons. Okay, now to get the internal force between B and C, we need to have another free body diagram, and so we're going to cut the section somewhere between B and C, and we're going to take this left side. We don't have to take the left side. We could just as well take the right side and do the free body diagram over there, and we could get the internal force that way. So it doesn't really matter, whichever is the most convenient. In this case, they're both equally the same degree of difficulty, if you will. So we'll just use the left side. So we'll have 12 kilonewtons going to the left, 18 kilonewtons going to the left. And so the internal force would be 30 kilonewtons to keep that in static equilibrium, just summing forces in the x direction. So all the way from B to C, this bar is feeling 30 kilonewtons. Okay, finally, we're going to take the section cut through CD and find the internal force in CD. You can probably almost by inspection know that it's going to be 22 kilonewtons. And we know that that's the easiest free body diagram to look at the left side. We could have just as well done a free body diagram over the whole section here, but why go to that much trouble if you can just look at the right side free body diagram? So we have internal force of 22 kilonewtons. Okay, so here are our three internal forces, and we're going to take this information and draw what is called a normal force diagram. So the reason we do this is that we want to make sure that we're capturing where on the structure the maximum and minimum forces are occurring in the bar. Now, in this particular case, all three segments are in tension, and so we all have positive numbers here, but it could just as well have one or more of these sections going negative, okay? Which would mean that that section would be in compression if it's a negative value. So now at a glance, we know that section BC is carrying the largest internal force. And since each of our segments have the same cross-sectional area, we're going to focus our attention on section BC with our normal stress calculation. So we're going to take the 30 kilonewtons, we're going to divide by the cross-sectional area. That's our formula, P over A, and we're going to calculate the normal stress in section BC. Now, I want you to pay a little bit of attention here to the units, because this is where often mistakes are made, and I encourage you to take the time to work these problems in a way that will minimize your potential from messing up the calculation, either with your units or just getting the numbers wrong. So what I recommend is whenever you're working problems with SI units, to use newtons and meters in your stress formula or your deflection formula later in the course. And if you use newtons and meters exclusively, so if you convert this 30 kilonewtons into newtons by converting it to newtons, that would obviously mean to multiply this by 1,000. You would have now the numerator in newtons, and the denominator would be in units of meters. Now, remember, in the problem, it was given that the depth was 35 millimeters and the width was, or the thickness was 10 millimeters. So these units here are those dimensions converted into meters. And so if you're not comfortable doing that, I recommend that you take the time to practice calculating these dimensions and forces into the proper units of newtons and meters. Later, as we talk about the imperial unit examples, we're going to be using kips and inches exclusively. And if we do that, we'll keep everything in the proper units for us. Now, if you do this calculation on your calculator, you're going to end up with a very large number here, okay, with lots of zeros and so forth. And you'll see that the answer has been written as 85.7 megapascal, okay? And so this is very similar to the type of format of a problem that you might have on the exam, where I will ask you to give the stress, for instance, in the maximum stress in megapascal units using 3 significant digits of accuracy. Okay, so this would be the answer that you would need to write down. It's very important that we do not write down an answer with more significant digits than we perhaps know the problem to be. There's always error in measurement, thickness and width and so forth, or maybe even the forces are not known to the precision that the problem may imply. And so we don't want to write out an answer with a whole lot more significant digits. In fact, maybe even 3 significant digits here might be stretching it a little bit. Maybe it's a little more appropriate to use 2 significant digits. And in that particular case, obviously the answer would be 86 megapascal. But this would be the answer if the solution is required to be to 3 significant digits. And so now we can kind of visualize that normal stress in bar BC, 85.7 megapascal. Here's our internal force and the dimensions of our cross section, just to kind of bring everything back into focus, what it is we calculated and why we calculated. We have not calculated the normal stress in the AB segment or the CD segment, and that's because the problem was asking for the largest normal stress anywhere in the bar, and so this is the largest normal stress. Okay, so let's shift gears just a little bit and now talk about shear stress. And like the name implies, you tend to have a shear failure like we see here. So we're applying an external force. This is the way you want to think about this is this segment here and this piece right here. Maybe think of these as rigid blocks, and we have a piece of metal going across, and we're pushing down on this surface, and maybe we're even pushing down on something that's distributed over here. So it's a single force, but we're pushing it all down. And the way that this plate or member is going to fail is going to fail with what are called shear planes here on each side. Okay, so we develop shear forces in this member to balance out the external force that's applied here. So these are the internal forces, V and V here, and that is what we're going to investigate, are the stresses that develop as a result of these shear forces. Now, in this particular case, we have a situation where the applied force is resisted by 2 shear planes. Okay, so we call that double shear. We're going to find with some examples here in a moment the difference between single shear and double shear and how that affects the calculations a little bit. Okay, so you always have to visualize the failure condition and understand the difference between single shear and double shear. All right, so let's say that we have a magnitude of shear force on each face, and just like we visualized before with our normal stresses, these shear stresses develop where we have the shear force. Okay, now in the textbook and in almost any reference you find, whenever shear stress is discussed, there will be this Greek letter tau that's used, okay, to distinguish the sigma for normal stress from the tau value of shear stress. Okay, so it's important that you recognize these are not just arbitrary Greek letters that are being thrown out, and you need to use sigma when you're using normal stress and tau when you're talking about shear stress. Okay, so let's come up with an equation for the shear stress in this particular case. We know it's related to the shear force. And so let's begin to kind of look at an individual area on this face like we did before. And so what I've blown up here is a face. We envision a little cross-sectional area here on this face. This would be the shear stress that develops on that face. And we have some fancy subscripts here, but we very quickly dispense with that and just use the tau values here because these are all equal. We're going to find out a little later in the class why all these are all equal, but for right now, all we're really looking at is this shear stress on this face. Okay, so this shear stress here is the same as this shear stress here. Okay, so this shear stress acts on an area, and that area is delta x times delta z. Okay, so if we take the shear force or increment of shear force, okay, that's acting on that area, okay, and we sum up all of those, okay, if we sum up all of the incremental shear forces and we sum up all of these little areas here that have been blown up, sum up all of these little areas across here, we will end up with just the total shear force, V, divided by the cross-sectional area. Now this equation looks very similar to our first equation, doesn't it? And in fact, you know, in many ways it's the same equation. It's just that we're talking about shear stress instead of normal stress. Now we will look at other equations for normal stress and shear stress as we go through the course, but for right now, this is kind of the simplest expression for shear stress, to just take whatever shear force is on the face and divide by the cross-sectional area, and that will give you the shear stress. Again, the units are consistent where we would have some sort of force units divided by area. So maybe this would be in newtons per meter squared, which would be Pascal, or it would be in, say, kips per inches squared, and those would be the units on tau. Okay, so it's important to know that these will have units of force over area. This will be in units of force, for instance, newtons or kips or pounds, and these would be units of area, meters squared, inches squared, that sort of thing. Okay, so let's now apply this to an example, and this structure looks probably something familiar to you from your statics class, and you may have wondered, why did we go to all this trouble to find, you know, the force in this cable or the reaction forces? Well, we're going to find out in this class, you know, why we do that. Now, before we get started, I want to point out that this connection is different from this connection, right? You see that we have two plates coming across with the pin going through each of those plates, and then it goes through the web of this beam. That's what this portion is here. So what this picture is the view, the aerial view looking down onto this corner, and then this is a side view of this connection. And so here's my cable coming down, and then we have one pin going through the web here. Okay, so this configuration is going to have a big impact on the shear stresses in these pins, and we're going to find out with this example how to handle each of these conditions. Now, this pin right here has a 20 millimeter diameter, and this pin over here has a 30 millimeter diameter. It's important to kind of distinguish the fact that we have a smaller pin over here than this one, okay? It's going to be evident later why we need maybe a 30 millimeter pin over on this side. Okay, so in order to start the problem, just like every other problem in this course, we have to do the work that you did in your statics class. We have to know the reactions, the internal force of this member, we have to do this work and use our statics equations, summing moments about point A in order to get the force in member B. And so you would get 12.5 kilonewtons. It's important that you go back to your statics class, refresh your memory on how this equation is developed. And it's not the purview of this course to repeat your statics class. So what you want to do if you struggle with coming up with these equilibrium equations is just go back and restudy that material, practice these problems of how you find these forces, okay? Because it's just a matter of writing the free body diagrams and applying your equilibrium equations that you learned from statics. So for the two-dimensional problems that we have here, we're going to use the summation of moments with the axis coming out of point A. And so that's just the 4/5 component is the vertical component of this force, and times the perpendicular distance of 6 meters. And then this is the 30 kilonewtons times 2 going in the opposite direction. And so those are the only forces that go into this equilibrium equation, because summing moments about point A, we don't have to concern ourselves with AX and AY. We can solve for FB directly. Okay, so our other two equilibrium equations are some of the forces in the X direction, where you can get the AX component of the reaction, and summing forces in the Y direction, you get AY. Okay, so we know that these are the X and Y components of the reaction force, and we're going to use this information to look at the average stress in this pin, the average shear stress, and we're going to look at the average shear stress in this pin over here. Okay, so whenever you see this word average shear stress, that's just what we've been talking about all along. These are assumed to be a constant shear stress over the shear areas, and so that's what they mean by average. Okay, it's nothing fancier than that. Okay, so we want to know the true or the real force that's on this pin. We have two components, so we need to find the resultant in order to look at that shear stress on this pin. And so it's going to actually be occurring along a direction here that is the hypotenuse of this triangle. So if we bring this vector over to here, we can then draw the hypotenuse of that triangle, and the magnitude of that is all we need. We don't need to know the direction of it and all that sort of thing that you did in your statics class. We just need to know the magnitude. So we can simply just take each component and square it, sum them together, and take the square root from the Pythagorean theorem. We get 21.36 kilonewtons. So that's what this force is that's acting on this pin, and it's being resisted by two shear planes. So we have a shear plane on this end and a shear plane on this end, and that's because we have these two plates for this double shear condition. So it's always important to recognize that you have either double shear or single shear. If you have double shear, you get to divide this force of 21.36. You get to divide it in half, and you only have to design it now or come up with the stresses based on the 10.68 kilonewtons. So now we apply our V over A equation for the shear stress, and we get the following. Okay, notice everything has been converted into newtons in the numerator, and in the denominator, what this equation is simply pi over 4 times the diameter squared, okay, in meters, and you'll end up with 34 megapascal. Now, you could use pi r squared for your area equation. That's fine. You would just need to make that 0.01 meters for the radius, or you can use the pi over 4 times the diameter and not have to worry about that. Either way, you're going to get the same cross-sectional area, obviously, in the denominator. So that would be the average shear stress in this pin at point A. Now we can go over to point B, and we see that that connection is different with the cable coming up. We have the pin going through it, and throughout the thickness of this, we're going to find this force in the cable, which is 12.5 kilonewtons. There's going to be a shear force on that pin of 12.5 kilonewtons as well. So with this situation, we have what's called a single shear connection, and we do not divide anything by 2. There's only one shear plane for this particular problem. Sometimes it's a good idea to really blow up that picture and really look at that. What is the shear that's happening on that bolt? And you realize it's a single shear situation. So now applying the V over A equation, we get the following calculation. Notice the diameter is different with that particular pin. It's 0.03 meters, and we get 17.7 megapascal for the shear stress in that pin. Okay, so these would be what are called analysis conditions of this structure. We haven't done any design at this point. We're just really analyzing what are the stresses in the pins. In order to get into design, we need to talk about what are called allowable stresses, and we'll talk a little bit about a factor of safety. Okay, so we can use our normal and shear stress equations, and we're going to introduce a factor of safety, and every factor of safety is a value greater than 1. Okay, so it could be 2, it could be 3, it could be 2.5. It's just a number that's greater than 1. And very often in this class, I would give you what that factor of safety is going to be for that particular condition. Now, in the real world, so to speak, your supervisor, your boss, whoever you work for, might tell you to design it to a certain factor of safety, and you would use that particular value based on maybe the standard that's used in that industry or some other sort of standard way of coming up with that factor of safety. Basically, what we're saying is that we have some sort of failure condition, and we want to make sure that we never exceed or have any stresses that get up to that failure condition. In this particular case, it might be the normal stress. So we would have maybe a failure condition of a normal stress of, say, 50 kips per square inch, so 50 KSI. And we have a factor of safety of 2. And so obviously, the allowable normal stress that we would be designing to for that particular case would be 25 KSI. So that's just to make sure that we never come close to that failure normal stress condition. Same thing with the shear stress. We could have some failure shear stress condition, and we would divide by a number greater than 1. And then in our design, we would make sure that the components that we were designing never allowed for a stress to go above this value, this allowable value. Okay, and then that's a way to really make sure that that the structure performs as we would want it to. Now, a lot of things go into why we have the different factors of safety. If you think about it, there's always a certain variability that is associated with the magnitude of the load that you might have on a particular component or structure. Sometimes we never know with 100% certainty what the load is going to be, and it could be actually higher than we would expect it to be. Conversely, we could also have our material properties having less strength than we thought. For instance, the material just didn't perform at the level that we wanted it to, and it's actually weaker, for instance, than it actually we thought we had for that particular material when we did the design work. So there's all these sort of variables that go into it. And then we might actually make the factor of safety a larger value, just simply because if that particular component were to fail, there would be this catastrophic effect. In other words, it would be a really major failure. Maybe it would lead to loss of life or injury in the person using that or occupying that structure. And then maybe there's some other components that maybe if it were to fail, it would be a minor inconvenience, but it certainly wouldn't lead to anything major happening. And so we might assign a lower factor of safety for that particular component because it's just simply not as critical as some other point. So as you go through your design classes later, you'll probably learn more about this idea of factor of safety and how in your particular industry we look at factor of safety. Like I said, this is kind of a first generation of design philosophy, but it's a really good place to start because it's kind of a nice, convenient, straightforward way to think about design, that we have some sort of failure stress and we divide by a factor of safety greater than 1 to make sure that the actual stresses that we have in the structure are never larger than these allowable values. Okay, so here's a simple example of a design example, so to speak. And maybe what we're looking for here is the embedment length that would be needed if we had this embedded, say, in concrete, or maybe this is a nail and it's embedded into wood. And we want to make sure that it's embedded far enough into the material such that if you were to pull it out, it would not come out. Okay, so this might be how you would go about determining the embedment length. Okay, so we would then maybe assign some allowable shear stress to develop all along the surface here of the embedment surface. And obviously, if we apply a force P, there's going to be a shear force that's going to be, if we add up all the shear around this face, it would equal to the applied force P. Okay, so there's some diameter that's already known about this particular rod, and there is a force P that we know, and there's an allowable stress for that material, for that wood or that concrete, and we could then determine the embedment length. Okay, so we just simply take our equation, our P over A equation, and we kind of rewrite it in the following form. So we bring the tau down to this side, to the denominator, and bring the A over here. And the A in this particular case is the surface area, okay? So the surface area is the length of the embedment times pi d. Pi d is the circumference multiplied by the length, and that would be the area. So with these two equations, we can actually now determine the length L. And it is just simply, so substitute this over here for A, and then bring the pi and the d down to the denominator, and now you have an equation for the embedment length. So whatever your force P is, whatever your allowable shear stress is, and whatever your diameter, you now have a formula for the embedment length. Very effective equation, just now knowing what the allowable shear stress would be. And maybe that would come from testing, and we had some sort of failure condition at a certain shear stress value, and you divide by some factor of safety to come up with your allowable shear stress, and now you have an embedment length equation. Okay, or maybe it's a base plate situation where you have this base plate, it's sitting on a concrete pad, for instance, and this concrete pad can only withstand a certain amount of compressive stress. And so we want to come up with maybe the dimensions of the base plate to prevent failure of the concrete below the steel base plate. Okay, and we would just simply use this equation here, whatever the allowable compressive stress is here, divide by the force P, and that would give us the area that we need for our base plate. And we could get the proper dimensions for our base plate. And in fact, in actual steel design practice, this is very similar to what we do as one of the checks for the design of that base plate. Okay, or we could use a shear stress sort of situation. And in this particular case, we have a plate that's taking a load, that's transferring load from this plate to this plate, and it's being transferred through the shear of this bolt. And so if we were to blow up this bolt and look at the bolt, the shear plane would be here, and this would be the area that the bolt is acting on. And so we can use this equation here to come up with the area of the bolt. Now, obviously for design, that would translate into the diameter of the bolt that you would need for design, okay? So there would be some sort of allowable shear stress on the bolt, and there'd be some applied force that we see here from our applied forces, and we could come up with the required area for our bolt. And this is also very similar to what is done in design for a shear connection for a steel structure, for instance. Okay, so we're using what we know about the allowable normal stress and allowable shear stress, and we're using it in a design setting. So let's get a little bit more specific, kind of tying back to our original example. And what we want to come up with is the design for, we want to determine the diameter of this pin, okay, at point B to the nearest 1/16 of an inch, where the pin material has an allowable shear stress of 10 kips per square inch, okay? So here's our structure. It looks a whole lot like a statics class type of structure. All we need to do in this particular case is find the force in member BC, because we know that particular force is going to be transferring through our pin here at B. And if we sum moments about point A, we can find the force in member BC to be 9.238 kips. Notice I'm keeping 4 significant digits for now, just to keep plenty of accuracy in the calculation as I go forward. I can always reduce that down a little bit later as I come to my final answer, okay? So that force is in the member here, and it's going to be transferring that force over a double shear situation. That's what this picture is trying to represent here, is that we have a double shear situation. And so the actual shear force on the pin is not the 9.238, but in fact, it's half of that. It's 4.619. Here is my area, pi over 4 times the diameter of the pin squared, and I'm equating that with the shear stress of 10 KSI. So notice all of my units here, these are in kips. These are in kips per square inch. So whenever I solve for my diameter, solve for D, I get 0.7669 inches. That's the required diameter of that pin. Now we have to go back to the original problem, and we have to think about what we're doing here in a design setting with the allowable stress. And it's very important that you pay attention to this particular part of the problem. We cannot allow our pin to ever have a stress larger than 10 KSI. Okay, so when you get an answer like this and you need to design it to the nearest 1/16 of an inch, you might be tempted to say, let's round that off to 0.75, like we normally do, or we round it, in some way to 0.77, or we look at it that way and we go, well, that's not really helpful, because whenever we have a pin, it can only be manufactured to a certain tolerance, and whoever's making these pins tell us that we can only make these pins in increments of 1/16 inch increments. Okay, so we can't just say the answer is 0.77 inches. We have to give the fabricator the diameter of the pin in 16-inch increments. Okay, so 1/16 increments. All right, now we need to make sure though that the stress never goes above 10 ksi. So I want you to think a moment about what diameter you would specify, where the diameter would still be in where you have a 16 in the denominator. Okay. Okay, so if you try 12/16, you get 0.75. And if you use 13/16, you get 0.8125. Okay, so let me say that again. If you use 12/16 or 12/16, you get a diameter calculation of 0.75, which is pretty close to that. Okay, and if you use 13/16, you get 0.8125. Between those two, which one, okay, will give you your stresses always below 10 ksi for your shear stress? Okay, can we use the 12/16, or do we have to use the 13/16? You can actually put those numbers into your calculator over here. So you could put in the 0.75, which would be the 12/16. You can put that, square it, multiply it by pi/4, do the calculation, and you will calculate a value that is greater than 10. Now, if you use the 13/16 for the diameter, that would be a diameter of 0.8125. And if you square that and multiply by pi/4 and put that in the denominator, you will calculate a value less than 10. Okay, so hopefully that now answers the question that you must specify the 13/16. You have to use that to make sure that your stresses are below the 10 ksi. Okay, so go ahead and calculate that stress. You'll find that it's less than 10 ksi. So your final answer for this problem would be 13/16. And that's how you would give the final answer, because it's asking for the nearest 16th of an inch. Okay, so you're not putting a fraction here, you're actually putting your answer in this format.